Hello, everybody. Thank you for joining us tonight in another Tech Talk. Tonight, we have Nick Krug, and he will be talking to us about database modeling. Before he begins, let's all unmute and give him a round of applause. Thank you, everyone. Without further ado, Nick, take it away.
Thanks, Cody. Before I begin, I'd like to thank CodeSmith and SingleSprout for sponsoring this Tech Talk. So just to level set a little bit about the purpose of a database, what we're trying to do here is with using a database at all is to store and organize information so that we can apply it to some sort of purpose. We need to design or model our database so that it's simple to store what we need and to retrieve it later. So today we're going to be talking through a simple way that we're going to be building a database model, specifically focused on transactional data for a small or medium business or a startup. And then we're going to get into what happens when our database model gets a little bit more complex, and how does that change how we approach modeling. So starting with the simple example, we need to build a database that reflects the real world so that it's going to be usable and easy to store. So we're going to do that by modeling our world. And we do this by starting at a very high conceptual level that is very abstract. And we're slowly going to get more and more concrete until we're actually able to build out our database. So let's kick it off with the conceptual model. The basic purpose of this is to align between the business side of the house and the technical side of the house on the entities and the relationships between them. You're going to see that the conceptual model is very abstract. It's easy to understand, and it enables this lockstep alignment so that everyone knows exactly what we're trying to build. The central question that you're trying to ask with a conceptual model is, what are the important nouns to our business and how do they relate to each other? So we're going to start with a Seedly, a standard e-commerce shop that focuses on gardening supplies for hobbyists. So what are the nouns we care about? And we care about our customers. And we notice that customers can relate to sales in that one customer can have many sales. Each sale can include many different products, and each sale is also going to have one or more shipments. So you can see how we're defining our nouns and describing the relationships between them. Once we have this sort of lockstep alignment on our concepts, we can then formalize our model by bringing it down to the logical level. So here, we're actually not only describing our entities, but we're describing the attributes of them as well. And we're describing their relationships in this syntax that's a little bit more formal. And this is called an entity relationship diagram. You can see here an example that we have our user table. It has a bunch of different attributes like name, phone number, and so on. And one user can have 0 or more, which is what this little symbol means, addresses. And as a result, the way that we have to model our data is that each address has to link back to the correct user via a foreign key. The other thing that we're trying to do with this logical model is normalize data so that we have a single source of truth. And we're thinking very carefully about when we need data, when we allow data to diverge, and when we need it to stay in lockstep. So we can have each item in an order has a product that it's referencing. Do we want this product name to be in the order item? In other words, if the product name changes, do we want that to change in all the order items or not? And is it a problem if those two things start to diverge? If we think, actually, that is a problem, we need the order item to reference the current name of the product, we really don't want to put the order item in here because this could lead to bugs where we are showing the wrong name for a given order item. So this is kind of how we build out this logical model. But notice that this is still fairly readable, and this allows us to maintain that lockstep between the technical and business sides of the house. Once we have a logical model built out, we can then translate it to something that is no longer really human readable, which is this physical model, where we are defining the final database structure. So this is going to include database-friendly names. It's going to include data types, in this case, for Postgres. It's also going to include metadata and implementation details. And if we have built this with appropriate software, this can actually be exported directly as a series of SQL scripts that we can use to fully build out our database. So we can take a look now at some of the modeling tools that we might use. There are paid tools such as Lucidchart and Vertibello. But there are also a number of open source free tools that you can use that work with many different kinds of databases and that allow you to, again, get that export to SQL scripts. My favorite of these is DBSpy, which is still receiving regular updates. So now that we basically have a fully built out database, what are we doing with it? Well, we have optimized our database for this left side of things, the transactions. These are the small reads, writes, and updates that we're going to need in order to deliver on our core business operations. So the databases that we select, that you would select for this, Oracle, Postgres, MS SQL, et cetera, they're all optimized for working with single records quickly. These are all your OLTP database or online transactional databases. On the other side of the house, we also have our analytical use cases. So these are going to be more complex queries that we need to support business decisions and allow us to see how our business is performing, see whether we're meeting our financial goals, and so on. However, our OLTP database is going to work fine for both use cases. It's just that the analytics one is going to require joins across many different tables and could be pulling millions of rows. But how does this change if Seedly were to take off? So let's say we open up new product lines, we support international shipping, we introduce third-party sellers, we create cloud services, which is of course customized watering and harvesting schedules based on local weather conditions. It's clear that Seedly's competitive advantage is actually coming from our technology rather than just the fact that we're selling seeds. So we need to be able to scale our engineering team and our platform in order to be successful long-term. So the first thing we do is, of course, we rebrand. Nile is a much better name than Seedly. And because of course the Nile floodplain is one of the most fertile areas on Earth. But the other thing that we do is we're going to re-platform to microservices, where instead of having a bunch of different modules or a bunch of different pieces of our code base that are all hitting a single database, each one is going to have its own little database. And they're going to talk to each other through APIs rather than querying each other's databases directly. So this is very different. It's very powerful in that it allows us to isolate teams to isolate their own work from everybody else so that they can make decisions about their own product and about the way that their technology works without affecting any other teams. However, it changes the way that we need to think about our modeling. So transactions still stay relatively simple. With a single database, the way that we would handle that is we would place an order. It would create some items in our database. And then a shipping module, when it's time to ship that order out, it's going to go pull all of the most recent orders that have not been shipped yet, and it's going to turn those into tasks. Very easy. And with the microservices world, what's going to happen is the orders microservice is going to push down orders and items into its own database. And then the shipping microservice is going to make a GET request. And this orders microservice will have an API that allows it to send over all the latest order items to the shipping microservice for it to then store in its own database, work through the shipping queue. However, what about analytics? Well, this is a little bit more complicated because as I said before, analytics queries can take, they can cross many different tables and pull millions of rows. And now those tables live in multiple different microservices. How are we going to handle this? How are we going to get our data in order to be able to report on what's happening within our business? Well, we have a few different options. We could query microservice databases directly. The problem is teams need to be free to make changes to their schema or even to embrace a completely different database technology or engine without breaking other people's workflows. But suddenly when they make these changes, our reports stop working. This violates the separation of concerns, which is the main reason we embraced microservice architecture in the first place. So that's not going to work. The second thing we can do is call every API endpoint we needed to, right? So let's say these 10 different databases lived in 8 different microservices. We could just call each microservice. And even if their database schema changes, they're still going to be fulfilling the same API contracts. We'll be able to get our data back. But this is going to be incredibly slow and complicated. You lose all of the advantages of using a database engine, and you have to build these really complicated pipelines for every single report you're trying to create. Data won't be timely. There's really only one way of getting data from microservices into a usable reportable store, and that is having each microservice team responsible for pushing their own data through something called a change data capture process. And this is going to tie into event sourcing, which is something we heard about recently, through a broker such as Kafka. So all these microservices might be publishing their own topics to Kafka, and then making sure that they are that they have database that a database is subscribed to all those topics to pull their raw data into a data lake. And this is where we can actually get away from our online transactional database and incorporate an online analytical processing database, an OLAP database. So these are optimized for volumes. They can do tons of writes, huge amounts of write volume, but they're not optimized for the kinds of very small transactional reads that we would need in our transactional database. But the reads that they support are going to be giant. There are 4 major vendors in this space: Amazon Redshift, Microsoft Azure, Synaptic Analytics, Google BigQuery. Notice that these are the 3 big cloud providers. So you're basically going to choose your cloud provider and be stuck with either their product or Snowflake, which works nicely with all 3 of them. So notice everyone's running their, pumping their own raw data into the data lake. And if you're going to be pulling millions or billions of rows, and you're going to be writing, say, thousands of lines of SQL because you're trying to fit all this raw, disorganized data into something that resembles a useful report, you're going to run into major cost issues. So we need a format that's going to allow us to make all this raw data usable. And this is where we get into a new concept called ETLs, or extract, transform, and load pipelines. The goal here is that you extract the data from your raw data lake, you transform it into a usable form, and then you load it back in, either to your data lake, which can turn it into more of a data warehouse, well organized, or you can put it into another store entirely. ETLs are kind of awesome because they democratize data modeling. When we were creating our OLTP database, it was data engineers and architects who were driving that effort because they needed to make sure that the database could grow with an expanding business. They needed to think about future use cases. They needed to think about speed and performance. But we have now disaggregated our transactional data needs from our analytical data needs. So now we can just let engineers and analysts and data scientists kind of operate independently based on the specific business questions they're trying to answer. And there are these ETL tools that have very friendly GUIs for non-devs. They let them monitor the status of their jobs. They let them do scheduling, and they let them support ETL dependencies, where basically you would have a chain of different ETLs, each depending on 1 or more prior ETL jobs, and you would run through the entire chain to get your completed data. There are a few different players in this space. There's Apache Airflow and Informatica, which are very friendly for non-devs, although version control can be a challenge. And then on the more technically advanced side of the house, you have dbt, which is not super user-friendly for non-devs, and AWS Glue. And both of these support configuration as code support with native Bitbucket and Git integrations. So we have our ETLs, and we're trying to get data into a usable form. What does this form take? Are we going to try and rebuild the same kind of model that we're using for an OLTP for our basically transactional processing? We don't really need to. We don't need to model the real world in the same way. Instead, we can think about the kinds of complex analyses that we're trying to do and create models that facilitate these analyses. And this is usually done through a star or Snowflake schema. This is a fairly abstract concept, so we'll get into it a little bit more. But the general idea is that there's a single set of facts or metrics at a certain level of granularity that you're trying to understand more about. So think about your sales, think about your users, think about specific events that might be happening in your business, and you want to understand them in context. And you do that through basically building out these dimension tables. So this is obviously super abstract. I'm sure that y'all are feeling a little lost. So let's get into a slightly more concrete example. Let's say I'm an analyst trying to answer the question of the product categories comprising 80% of physical product revenue, so trying to ignore the kind of long tail. What are the main drivers of sales from new customers? So this is a very deep question. There's a lot to unpack here. We can see that the thing that we care most about is sales. So our fact table is going to be all around sales. What is the revenue that we're generating? When did the sales happen? What specific items were sold? And we want to then understand that with a bunch of different pieces of context. So we need to add a bunch of filters related to products, categories, physical, and then we need to understand what is driving those sales. So we don't exactly know what data we'll need. So let's grab a whole bunch. So we're going to basically use all of these different dimensions in order to filter, group, aggregate, sort, which is colloquially known as slice and dice our sale items and be able to answer this question. So if we look at what a logical star schema model, going back to Nile, we can see that we have our sale item table, and it's got a bunch of other ID columns that are each referencing out to one of these dimension tables. And we need to make sure that the sale table is always at the greatest level of granularity. For instance, you can have multiple sales of a single product. You can have multiple sales from a single user. You can have multiple sales from a single dimension. You need the granularity to go this way because otherwise you can end up duplicating data. So yeah, this is generally how we would model data so that we can easily answer some of the really complex business questions that are facing us. And I mentioned star and snowflake schemas. So just to quickly touch on that, a snowflake schema is just a star schema where the dimension tables can be broken out somewhat. So you don't need to denormalize everything into a single, like one single join out from your fact table. All right, so why not just throw everything into a single table? First of all, there is a good answer to that. The reason you want to create these kinds of dimension tables is because they can be kind of reusable components. This is something that you need to do and think about as part of an overall data governance strategy, because you want to make sure that your analysts don't have to answer or reconstruct what's going on with the raw schema over and over and over. So ideally, they're creating these useful reusable components, but we don't really need things to be in a star or snowflake schema once we know what the definitions are. And Druid asked themselves this question. Back in 2011, they created a database engine that has almost no concept of joins whatsoever. They could not do a join before 2020. And even still, joins are extremely limited. They're really just for lookups. But Druid can handle 100 plus dimensions and 100 plus metrics in a single super wide, very flat table with absolutely insane read and write performance. It can handle massive scale, and it's widely used in Fortune 500 companies, including Netflix, Reddit, and Airbnb. And as a result, Druid is often used to power real-time dashboards such as Power BI and Tableau. And really, that's the entire point of getting all of this data into this analytics format, is so that we can derive business insights with amazing dashboards like this, which would be incredibly difficult, if not impossible, to get at with a typical OLTP database. All right, so takeaways. You want to start by modeling your world. That's kind of where you want to start at a high level. If you're operating a new database, if you're starting a new business, you want to start by building out those concepts and then getting to your sort of logical levels with your entities, attributes, and their formal relationships, and then building out your physical database model. And on that note, you want to start with a simple OLTP database, because as we've seen, microservice architecture comes with major technical complications when it comes to being able to report on your data. However, you want to also invest in analytical modeling when it makes sense, because this is going to give your business far better capabilities to derive insights when you've captured all the lower hanging fruit and you're trying to figure out how to make sensible business investments. We've really just scratched the surface on database modeling. Here is a little bit of further reading if you are interested. And please feel free to reach out to me if you want to talk more about this on LinkedIn. Thank you.
What an excellent presentation, Nick. Let's all unmute for a moment and give Nick a round of well-deserved applause. Wonderful. Does anybody have any questions? And if you do, could you please use Zoom's raised hand feature? If not, let's unmute and give it up for Nick one more time.